Today, what we want to do is we want to talk about OTV, Cisco's overlay transport and virtualization. But before we do that, what we've got to do is talk about, what is exactly the point of overlay transport and virtualization? It's actually really, really simple. But what I like to do is I like to pull out this really expensive whiteboarding utility. I don't know if you've ever seen this one, PJ, but it does the job. So what's the whole point of overlay transport and virtualization today? Right now, what we're seeing a lot of is multi-data centers and the need to be able to take, let's say we've got a host server at both locations, and I have a virtual machine that I want to move from location, we'll call this A, to location B. Well, to be able to do that, if I want to vMotion that over to another host server in another location, we have a problem. See, vMotion is very highly dependent on layer 2 VLAN association. What that means is that this host server's interface and this host server's interface, first of all, must be in the same VLAN, but second of all, it must go across a layer 2 environment. But wait, over here, what's in between these two data centers? Layer 3 environment, right? So that's gonna break any vMotion that you're trying to do from data center A to data center B. This is no good. So what we need to start taking a look at is building out overlay transport and virtualization. And just as a side note, hey, we could absolutely, if you wanted to, we could go dark fiber, right? EVPNs. There's other technologies out there that do this, but what I really like about OTV is the fact that with just a simple license, I can extend my data center or my VLANs to multiple data centers. The way that we're going to do that with OTV is over here, we're going to have our edge devices, and I'm going to go into this much more in detail in just a few minutes here, but we have our OTV edges. They have two major things that they do. The first one is to extend the internal VLAN. By the way, we call those extended VLANs. So this is an extended VLAN. The extended VLAN, what it allows OTV to do is these devices we call our OTV edge devices. Anytime they see traffic moving from here to here, they're going to know, hey, I should probably encapsulate that in OTV and send it across. But hold on, how does it know that? That's the second major piece. Whenever an OTV edge, for instance, learns a brand new device, and we're going to say that this MAC address is 1111, okay? What this OTV edge device is going to do is with OTV, we create essentially an ISIS neighbor adjacency. Yeah, it's like a routing protocol. So now instead of you updating routes, you know what you're doing? You're updating hosts. So anytime I learn a new host, I'd better go tell my neighbor about it. Now, this is really cool because now that MAC address at the other data center is in this guy's MAC table. And furthermore, it also maps it to the public side IP address of that site. So we'll just say it's A, sure, right? So this information right here is what we're going to tack onto the original frame. The whole point of this OTV thing, PJ, is the fact that when the original data comes through here, right? So we're just going to call this data. I don't want it to be manipulated whatsoever. I want to preserve the layer 1, layer 2 information so that it looks like the original data when it gets to the other end. That is super, super important. So the way that we preserve that is we implement OTV. This is called an outer header. So it slaps on an OTV header. This is the same thing that happens with 802.1q, same thing that happens with VXLAN, NVGRE, IPsec. These are outer headers that are being read as opposed to our inner headers so that they're not changing. So this OTV header has the source of B, his public site IP address, and the destination of A. So as it's bouncing around here inside the cloud doing its thing, it's being routed to this layer 3 address so that whenever it's received on the other end, that OTV header is stripped off, and we simply do a lookup for where is this guy located? Oh yeah, it's over here. Now, I would say that that's probably the 40,000 foot view of what OTV does. Let's go ahead and drill down a little bit here. So in this example, what they're showing you is the difference between the layer 2 and layer 3 environments with OTV. What we're doing here is on these OTV edge devices, they are extending this layer 2, as you can see here with this blue. They're extending this layer 2 environment through the IP network into another location. And again, I can't stress this enough. This is very, very similar to what you're seeing with things like VXLAN. So if you're, PJ, if you're familiar with ACI, that's exactly what the VXLAN does internally. This is also very similar to Fabric Path, if you're familiar with that. Very, very similar. The layer 3 is completely agnostic of how the layer 2 communicates. We don't care what the layer 3 is. We just care that the layer 2 gets across. Now, as I mentioned before, what we're going to do is you see right here, this MAC address 2233 is out G01. Okay, so it's out this interface. But what about this guy over here, 5566? Notice again, the MAC address over here in a different location is still in my MAC table. And notice it's not to a local interface. It's actually to a destination IP. That right there, when you do like a show MAC database, you're not actually going to see that. You're not going to see the IP. You're going to see like overlay 1 or whatever you named the OTV overlay. Yeah. So, and then there's the OTV configuration that specifies the IP info. But with that being said, let's look at some of the components. I know this looks busy, but it's not. There's not actually much going on here. The first thing is, obviously, we're going to have the edge devices. On those edge devices, they are going to have an overlay interface and an internal interface. The internal interface is where I can learn new MAC addresses as they send ARPs, as they flood, so on and so forth, right? The overlay interface is what we actually use to send the traffic to the devices, the end devices. The join interface is actually, it's a logical interface tied to the physical one that's used to do the encapsulation and send those LSA updates, right? So the join interface is really, you know, what's doing the magic. The overlay interface is just that physical interface that we're specifying, okay? Other than that, what ends up happening is these OTV peers, they actually create like a mesh topology dynamically or statically. I like dynamic because, you know, I'm efficient, not lazy. I'm efficient. And so it just makes it a lot easier when you set it to multicast. They just all start adding each other across the MPLS environment. Piece of cake. But again, you can do this statically if you want. The point is that they create an overlay network that we're going to start sharing end node information and encapsulating from one location to another with that OTV encapsulation. Keep in mind that the overlay interface is really, you know, it's like the physical interface, and the joint interface is more of the logic behind it. So control plane and data plane. Okay, all right. Well, the first thing that we have to do to start building this out is you got to discover the other devices inside your OTV network. Now, as I mentioned, you're going to have to build neighbor adjacencies. You can do that with multicasting, and we just enable multicasting, and it acts just like OSPF. So PJ, if you are familiar with Open Shortest Path First, you know ISIS, because guess what? ISIS was the predecessor to OSPF. The only difference was OSPF was running IP, ISIS was running NSAP at layer 3. They're the exact same thing. They both use LSAs. They both use the Dijkstra algorithm, 10 to the 8 divided by bandwidth and bits per second equals cost. They even use OSPF uses areas. ISIS uses levels, but they're the same thing. They're there to control your LSA propagation. So they're exactly the same protocol. It's just the fact that ISIS is a more open standard, so anybody can use it. So it utilizes multicast natively to create those neighbor adjacencies, just like EIGRP version 2, OSPF, BGP, right? It uses multicasting. Or let's say that multicasting is not permitted inside of your MPLS environment or your layer 3 transport network. You could statically assign this, definitely. For some reason, I'm brain freezing right now. It's a specific switch that you specify. It's called the adjacency server. You just select one of the edge OTV devices and you set it up as an adjacency server, and everybody just talks to him. It's kind of like a route reflector. We'll talk about it later. This is an example of using multicast. Pretty simple. We're going to set up all 3 of these sites for OTV. Make sure that you got your overlay and your joint interfaces configured. By the way, you do have to specify that it is set up for multicast. Once you do that, they're going to start blasting to each other across that this layer 3 transport network. So you're going to send an IGMP message, an OTV hello, in the form of multicast, and it's going to hit these guys. They're going to introduce themselves. Hi, I'm site A. Can you please respond to me? Oh, you're site B and you're site C? Cool. Now everybody knows about each other. Couldn't be simpler, right? Excuse me. Now, after that's done, these guys all have neighbor adjacencies, right? So IP, or we'll just say site A, knows about site B and C. So anytime they learn a new MAC address, just like I said, we're going to replicate that MAC address across to the other sites in the form of an OTV update. By the way, again, just keep in mind, this is an ISIS linked state advertisement. We just call it an OTV update to hide what's underneath the hood. But what's underneath the hood is an ISIS linked state advertisement sent in a multicast fashion. Pretty simple. Now, what about using Unicast? Let me move this out of the way here. Okay, so what about using Unicast? Okay, so what you're going to do is you're going to set up this thing called an adjacency server. Now, what ends up having to happen is you're actually, and I don't like how they do this, what you actually do in the real world, because I've actually done this 100 times, you set up the first site as the adjacency server. And then what you're going to do is you're going to go to this site and you're going to say adjacency server equals this guy's IP address. Bam. C introduces himself. A will replicate everything that it currently knows about. Then we're going to go to B. We're going to advertise adjacency server here to the IP address of this site. Again, what's going to end up happening is B is going to introduce himself. A is going to say, hey, by the way, I know about this C. If you get some time, go ahead and introduce yourself to C. So bam, now C knows about B also. So now they're fully converged, right? It's not a super complicated process. One thing, PJ, if you're thinking about doing the static Unicast version, I would give it, once you set down the configuration, I would give it about 10 minutes, right? The other option is that you can turn on and off the overlay interfaces, forcing them to re-acknowledge and re-unicast. But otherwise, yeah, it takes about 5 to 10 minutes. It's not like a super immediate thing. Now, as I mentioned before, yeah, since I over here on each one, well, actually on each one of these devices, don't I have the IP address of A and B? So whenever I am setting up an LSA or an update to send out, I already have the IP address of B and A. Instead of sending it as a multicast, I'm sending it as a straight up unicast. I'm taking the IPs that are in my neighbor table. I'm setting 2 unicasts one to each location. Bada bing, bada boom. We're updating those sites. All right, now digging a little bit deeper, as I mentioned, the OTV transport, it's all about having that header information inside of the data. So actually, this right here, the original layer 2 frame, this is all your data, your source and destination MAC, your 802.1q header, right? And actually what we do is we do have this thing called an OTV shim. This ends up becoming the overlay ID. Excuse me, sorry about that. This ends up becoming the overlay ID. So yeah, you're actually reusing what's in your 802.1q header, your VLAN ID, and utilizing it right here. Now, the other stuff that's super important is right here, right? We're going to put on an IP header. This IP header is the source and destination IP of the locations, right, of the OTV edge devices, their public side IPs. That way, again, as they're bouncing through the layer 3 transport network, we don't have to worry about anything, right? They're modifying these headers and not these headers. I like that. Now, another really neat thing that you don't have to do anything for. PJ, this is already set up for you by default. Forget about it. Don't worry about it, right? It's already set up. Because think about it. If we're extending here, let me pull this up here really quick. Think about it. If we're extending layer 2, isn't it possible that a loop could be created here and then simply be propagated across here to here? Happens all the time with dark fiber and EVPN. All the time. Yeah, because it's just straight up layer 2. But you know what? OTV, it has a hard stop right here. It does not allow spanning tree out the overlay interface. Period. End of statement. This is called fault or failure isolation. Again, yeah, we don't send BPDUs across that OTV environment. So therefore, even though they're the same VLAN, they're 2 separate spanning tree instances. So never shall the twain meet, right? They won't interact. They have the same VLAN ID, and the localized spanning tree can take care of any loops, but it does not send BPDUs. Therefore, it will not hook those 2 together and loop across multiple sites. Again, you don't have to do anything for this. This is already enabled by default. Here's another thing. The unicast storms. So again, BPDU stop here. The point of this is, see how I don't see MAC address 3 right here? Right? MAC address 1 is trying to talk to MAC 3. Well, what normally happens if we can't find something, PJ? We normally flood that out to everybody. Oh no, could that create another broadcast storm? Or in this case, a unicast storm? Absolutely. Not a fan of that. So again, you don't have to do anything. This is enabled by default. If it does not find the destination inside of the OTV edge, it is actually assumed that that device is not in any data center anywhere. Now, that brings us, PJ, I know what you're thinking. I can hear it. You're going, yeah, but what about my DHCP servers that their MAC address is time out of my MAC table? Oh no, now I can't have DHCP. Well, we actually have something for that where you can actually create a static entry. Unfortunately, that's the only way that we can really deal with silent hosts right now with OTV, is we actually build a static entry for the IP and MAC address for that DHCP server, so it never leaves the MAC table. Now, another thing that you can do is you can specify who can and cannot go across that OTV edge. As you can see here, allowed? No. Because these guys are internal. They're inside here, right? But what about MAC address 3? Is it at another location? Or do we want them to be able to talk to another location? We're going to go ahead and specify, yeah, we want to allow that communication. Again, all of this is set up except for the fact that you specify that MAC address and allow it through. Now, I know another thing you're probably thinking about is, okay, so layer 2 has a lot of flooding, it has a lot of broadcasts. So we just no longer have flooding and broadcasts? No, we do. Get this. This was one of the first advancements that I saw that kind of changed the game. I'm sure you're probably familiar with proxy ARP. That's exactly what this is doing. When you enable IGMP version 3 on this interface, it also enables snooping and ARP caching. So if I see an ARP request hit this device for, let's say, well, first so it's requesting IP address A. Isn't this already in our MAC table? Why would I send that ARP flood across here and then flood across there? If I already know about it, what's the point of doing it a second time, right? So guess what we're going to do? This device will respond on behalf of the remote server. Now, I do want to make a mention here that if you have not learned that MAC address yet, and you are permitting ARPs, then yes, that first ARP will go through, it will respond, but we will cache it because now we know it's a valid ARP request and reply, right? You kind of got to validate that before you send it, before it becomes a thing. One moment. Okay. Now, by the way, the ARP thing, totally done by default, don't have to do a thing. Multi-homing, it's all done by default, you don't have to do a thing, right? So with multi-homing, what you're actually doing is you're essentially load balancing VLAN traffic. So if I have two VLANs, one VLAN is going to use that top OTV device, and the bottom one's, or the VLAN 2 is going to use the second one. We call these authoritative edge devices. This is kind of like the primary or the active in a cluster. And this is, again, PJ, this all happens by default. You don't have to do a thing. I do want to mention here that we do have to enable what's called a site VLAN. Remember, I was talking about extended VLANs, right? Allowing VLAN 100 and 101 through the IP transport network. If you're going to do multi-homing, you have to specify a site VLAN and just make sure that these two, and it's literally OTV site dash VLAN 10, right? And then it clusters and multi-homes automatically for you, right? You just got to make sure that these two edge devices can see those VLANs. Now, as I already mentioned here, preventing end-to-end spanning tree loops, yeah, we're going to go ahead and make sure that broadcasts are not sent across here, right? Broadcasts stay local. This OTV mobility, this was the whole point. This was that first diagram that I drew up. You want to move a virtual machine. How does it work, right? Yeah, by the way, when you move a virtual machine from one location to another, it actually deregisters that MAC address from this MAC table and re-registers it at the new location. Another perfect example of this is Lisp. Now, this right here, this honestly, PJ, if you've heard of Q and Q, dot one Q inside a dot one Q, that's what this is. What we're doing is we're changing the VLAN ID so that when it's inside the core, it's called something else, so that we're preserving the internal. But yeah, not something that we do too often. Excellent. So path optimization with HSRP groups. Yeah, we support hot standby routing. But here's the thing. If you just set up HSRP, remember, they're multicasting across here. They allow multicast. I didn't say anything about broadcast. I said multicast. So if you set 4 of these devices up for multicast, they're going to multicast to each other. And what could end up happening is you could have an active standby listening, which means, get this, that if I want to go from VLAN 10 to VLAN 20 in this location, I'm going to have to go across here, get routed by the active edge device, and then be rerouted here. Now, PJ, I know you know there's something wrong there, right? That's not good. We don't want that, right? I want to be able to go to my local HSRP and then back down. So how are we going to fix this? So what you're going to do is you're going to filter HSRP hellos. So you're going to filter out the multicast address. You're also going to filter out the MAC address that HSRP uses for their virtual IP and MACs. So you're going to disallow those addresses from being shared across the OTV network. In that way, it's super simple. At that point, hey, they're going to create an active standby at each location. Bellissimo. That's what we're looking for. And yeah, this is just showing you that, yeah, instead of bouncing, it's going to go to the local. So cool. Okay. We're not doing a discovery. PJ, did you have any questions?
No, I think the big takeaway was the manual stuff to set up was hot standby you mentioned, and also that static MAC for like DNS or DHCP. Is that right?
Yeah.
Everything else is pretty much out of the box default.
Yeah, and just as a heads up, it's any silent host, so it doesn't have to be DHCP. Anything that just like sits on the network and doesn't talk for an extended amount of time, more than like 10 or 15 minutes, right? You're definitely you're going to statically assign that. And then yes, the HSRP groups, they're configured exactly the same. It's just now you're going to create a MAC ACL, a VLAN ACL, and then an actual IP ACL to deny that multicast address to leave that interface, right? The exiting interface,
right?
On both sites. Other than that, yeah, everything's pretty much default. It's a beautiful thing. It works really well. OTV, it takes about 4 or 5 commands and it's set up. So, groovy. So, any questions on that at all?
No, it looks great. This is specific to the Nexus switches, right?
It is.
Okay.
You know what? I think the ASRs can also do that, and there might be some ISRs that allow OTV, but I'm pretty sure like your ASR 9Ks can do OTV.
Yeah, the 9Ks, do they need special licensing to do this?
They do, and I don't know what that licensing is.
Okay.
I just want to throw it out there. Anytime somebody says licensing, I just go like this.
I gotcha.
Yeah. I'm not the guy who buys it. So like, it's not, I read it in one slide every class, so.
No, that's fine. That's cool.
Whatever. But yes, I do know that you have to have a transport license for the Nexus. So I think it's called a transport license in the ASR 9K also.
Okay.
Yeah. You have to have that license if you're going to do VXLAN with ASR 9Ks also.
Oh, so you do need one for VXLAN as well?
They're the same license. They're the transport license.
Okay, cool.
Yeah. But like your 5600s, for instance, the Nexus 5696, it comes with OTV and VXLAN 90-day grace period. So you can already use it. You just got to get the permanent license.
Cool.
By the way, while I got you here, PJ, are you guys doing ACI?
Well, so I work with an engineer and we are setting up VXLAN because we do have a DR and a data center, and we're running into that issue to vMotion, and to whenever we fail over, we have to put in static routes back, and like it's just kind of a mess.
Yeah,
but I'm not sure where he is at like setting all this up. So that's why I was like interested in taking this.
Yeah, for sure. So it sounds like from what you've got going on, OTV would definitely be what you're looking for in between the environments. VXLAN, I mean, that's the future. The only difference between what you're doing in ACI just does it for you. It just sets up the VXLANs for you, right? Here, you're doing layer 2, layer 3 VXLANs or route switched VXLANs, and it's kind of a bear, that configuration can be tough.